So let's get started reviewing Stoichiometry 2 mole concept practice. So continuing on our journey through stoichiometry, we have this unbalanced chemical reaction, a decomposition reaction, and we're going to need to balance that for number one. So let's go right after it and get those mole ratios, write those coefficients. A little more challenging, but we can do this. So when I look at this, I see that there's a parenthesis here, and there's a 2 here, which means there's 2 of everything inside. So there are 2 nitrogens, and I have 2 nitrogens. That's good. And 2 times 4 hydrogens means that there's 8 hydrogens altogether. The only place on the reactant side that has hydrogen is that water. So to get 8 hydrogen atoms, I'm going to have to put a coefficient of 4 here. Remember, don't forget that this is an application of the law of conservation of mass. And of course, this is all we're doing here is, figuring out what numbers we put in front we call mole ratios to balance this, to show that there's the same number of atoms and type of atoms on both sides. So we've got our nitrogens balanced, our hydrogens. There's 2 chromiums. Hey, we have 2 chromiums, and now we have 7 oxygens. Okay, well, looking over here, we have 3 oxygens, and then, well, each water has 1 oxygen, but having 4 there, by distributing that gives me 4. So the entire amount of oxygens on the reactant side would be 7, and that balances. So all I needed to do here was put a 4 on the water, and I am balanced. Now what does that mean? Well, that means, of course, that these other numbers are 1. You don't have to put them in, but it's a 1 to 1 to 1 to 4 ratio in terms of molecules. All right, the mole ratio of those particles. Okay, so let's go continue these questions here. So we balance the reaction with the smallest whole number ratio. So 1 to 1 to 1 to 4 ratio is the lowest whole number. Now, if I was to balance this and I had 2.5, I can just multiply everything by 2, but I don't have that scenario here. Is this reaction a redox reaction? Okay, well, to identify if a reaction is a redox reaction, I'm going to assign oxidation numbers. Now, there's a quicker way, and it doesn't always work, but I will do that first. Anytime you see an element standing alone, in this case, I see nitrogen standing alone, I know there's a redox reaction because I know that an element bonded to itself has an oxidation state of 0, or if an element is by itself like gold or magnesium. And if it's a 0 when it's by itself or a standalone, then it's not a 0 when it's bonded to something. So therefore I know that oxidation numbers have changed. That means electrons have been passed around. So that's the quickest way, but you don't always have a reaction where you have a standalone. So the best way to do this is to assign oxidation numbers, and we'll do that. I'm going to start with the nitrogen because I identified that to be 0 because it's just standing alone. Even though it's bonded to itself, it's standing alone. So now I've got to dissect what's going on in this salt. This is a salt. By the way, this is the ammonium. This is the ammonium ion. NH4 plus is a polyatomic ion. And this is the dichromate ion. That's Cr2O7 -2. It makes sense there's 2 of these ammonia ions because each one is +2. But how do I figure out the nitrogen in all of this? It's very, very helpful to look actually at the individual ions. So I'm just going to pull out that nitrogen comes from the NH4 plus. It's a really nice little easy way to attack something as complex as this salt. And what I'm going to do here is assign oxidation numbers just to this ion. We know the ion is +4, so what is the N in this +4? Well, the overall charge, I always write in the bottom. I can do this. I don't know why I can't, but it's here. And it's equal to +1. We know hydrogens are always +1, except when they're hooked up with alkali metals or alkaline earth. So this is +4 altogether because there's 4 of them. What number plus a +4 is +1? Well, +3. Okay, I'm sorry, -3. I can do this. All right, so a +4, I need a -3. All right, and that means there's only one N, so it's -3 altogether. So that means that nitrogen is -3. Game is over because now I know that there's oxidation numbers changing. But if you needed to identify who else is changing, I know the oxygens are almost always -2. There's a couple of scenarios when they're not, so that's not going to change. Let's look at the chromium. Okay, now the easiest way to attack the chromium here is to pull out the ion. Or if you have got a table where you can look up what these ions are, because if you see clusters, normally clusters of elements in a compound, it's normally going to be some sort of salt. And if you have a table or you memorized your polyatomic ions, it's easy to do this if you pull the polyatomic ions out. So what I'm going to do here is the same thing. I'm going to take a Cr2 O7, and it's got a -2 charge. It means the overall charge is -2. That oxygen is -2. There's 7 of them. 7 times -2 is -14. What number plus a -14 gives me a -2 overall? And this time I got it right, plus 12. But remember, there is a plus 12 for all the chromiums, but there's 2 there. So what's the charge per each chromium? Well, plus 6. There you go. So this chromium is plus 6. And what is the chromium on this side? Well, notice there's no charge here. The oxygen is -2. There's 3 of them, -6 overall. The whole thing is a 0. There's no charge there. So this has to be plus 6 for all the chromiums, but there's 2 of them here, party people. So each one is plus 3. So again, you didn't have to do all of this, but if this was an AP question and they asked you, hey, if this is a redox reaction, and cite a claim and evidence, you would say that yes, the claim is it is a redox reaction, and the evidence is that the oxidation numbers are changing. They may ask for specific, who's getting oxidized and who's reduced. Okay, we only need the individual charges here. So what's changing is the chromium. All right, so the chromium is going from plus 6 to plus 3, and then the nitrogen is changing from -3 to 0. And you can see that one number is going up, so nitrogen is going up in charge because it's losing electrons. It's oxidizing, and chromium is going down because it's gaining negatives. So the electrons in the ammonium dichromate is actually being transferred within side of that salt. Kind of cool. So the oxidation reduction is occurring within the molecule, or in this case within the formula, because this is an ionic compound. There's a positive ion and there's a negative ion. So it's not a molecule, it's a ionic compound that has a formula, and it has a repeating arrangement of this +1 and this -2. Okay, so in any case, just going over all these things. So is it a redox reaction? And you would say yes. And justify your claim, there are, well, I guess I'm going to be very specific, don't be vague. Nitrogen, okay, is I'm sorry, nitrogen is changing its oxidation state from, short-term memory's gone here, from -3 to 0. And chromium is changing from +6 to +3. And that would be your justification, okay, that we just did there. Determine the IUPAC name. Don't get crazy with the IUPAC. When you name a salt, we have 2 rules. If it's binary like sodium chloride, which is not the case here, we name the element in front like sodium, and then of course we add an IDE to this, in this case the nonmetal, so that'd be sodium chloride. In this case we have polyatomic ions, so this is not binary, it's a ternary salt, so you name the actual ions involved. This is the ammonium ion. This is the dichromate ion. And they stick together because of differences in charges. So this is the ammonium, okay? And again, if you have a table you can look at, for my students it'd be table T, but if you have to memorize them, that's something you have to know. NH4 plus is the ammonium ion, and then the Cr2O7 negative 2 is the dichromate ion. So ammonium dichromate. You name the polyatomic ions. The positive one goes first. Very simple. Okay. Any case, here comes some stoichiometry. So the first question states, from our balance reaction, calculate the mass of water that was produced theoretically if I had 87.4 grams of the salt that reacted completely. Don't lose credit. Get crazy here. This is a salt. It's made up of ions attracting each other, specifically the ammonia ions and the dichromate ions. Okay, we can see this reaction occurring here. It's a kind of cool reaction where it's oxidizing, reducing with itself. Also, so I'm going to write down what I have in grams of salt. So 87.4 grams, okay, of NH42 and the Cr2O7, and I need a subscript there. Okay, I've got grams of that, and we want the mass of water. So you're giving me some information about the reactant, and we want the water. So to go from this chemical to water, I got to do some stoichiometry. And by the way, I think I lost my ratios here. It was 1 to 1 to 1 to 4. So I know it's a 1 to 4 ratio. So what I'm going to do is I'm going to convert this into a how many number. I've got to go to moles. Why? Because, hey, this numbers that we found in these balance reactions, we counted. We're figuring out how many of these, in this case, molecules here or formulas here that we're dealing with. So it's a how many number. Grams is a how heavy number. So what I'm going to need is a formula mass. Okay, it'd be nice if they give it to you, and sometimes they do. And I say formula mass because it's a formula, it's an ionic compound. So in this compound, I'm going to do it right here. I've got 2 nitrogens, right? There's 2 nitrogens here. And so 2 times the atomic mass of nitrogen, I'm going to round off to 14, is 28. I'm going to find all the grams using the mole concept, using the atomic masses from the periodic table. And then I have 2 times 4, 8 hydrogens. Okay, and that's 8 times the atomic mass of hydrogen. I'm going to round to 1, I get 8. Okay, I have 2 chromiums. So I'm going to 2 times the atomic mass of chromium, and that is 52. Again, take out your periodic table. And 2 times 52 is 104. And then, of course, I have 7 oxygens, right? Right there. So 7O. And the atomic mass of oxygen is 16, so 7 times 16. And if you know your 16 times tables pretty well, you don't need a calculator. Of course, I'm pausing because I need one. Is a 112. And of course, the idea behind this, very simply, is that 1 mole of this formula has all of these individual moles of these atoms. Okay, and the atomic mass of each atom is the mass per 1 mole. So we're going to add all this up. 112 plus 104 plus 8 plus 28, and that gives me 252. And that's 252 grams per mole. Okay, I'm going to get rid of these arrows here because they're just bothering me. Okay, so party people, we're going to now use that value to, Christmas, got to get the eraser off, to 252. I should do that in red because that's what I just did, right? Yeah, 252, and that's per 1 mole. And here comes the stoichiometry. There is one of these NH4, or ammonia chromates, dichromates I should say, for every 4 water molecules. Remember, they're giving information about the salt. That, of course, that salt is the ammonia dichromate, and they want how many grams of water. But I had to convert to moles first, okay? And notice what I'm doing. I'm getting rid of the grams. I'm using my units in dimensional analysis. Now I'm going to get rid of this compound, and the units left standing are moles of water. That's great, but we don't want moles of water. We want grams. So I'm going to continue this. And last little piece, moles on top, so 1 mole on the bottom. If we're cool, we don't write the E. You can see I'm not that cool. And the molecular mass of water is 18. There's 1 oxygen, that's 16. Each hydrogen is 1. We should know that one. Okay, if you want to memorize some, they're fun, and there's some parties for that. Okay, so mole goes away. I'm left with what units? Grams of water. That's what we wanted, and let's go get that. Okay, get that that answer, and just take our calculator and multiply through. And dimensional analysis really helps here to keep yourself organized and cancel what you need to do. But understand, before we get the answer, we needed to go to moles first. We had to be in a unit that was a how many, then we can times it by the what? The mole ratio, right? That's important you understand that. And then once we got moles, and we converted back to the grams of the new compound that we just solved for. Okay, so in any case, 87.4 divide by 252 times 4 divide by 1 times 18. And what I get, party people, is I get 24.97, and that would be grams of water. All right, now hold on to your ponies for a second. I gave you 3 significant figures. In this conversion, we didn't measure any of this except for the original grams, so we should have 3 sig figs. Hey, this 7 is going to move this up to a 0, so this becomes 25.0. Okay, if we're going to round to 3 sig figs, 25.0. When you're doing a conversion like this, you're not multiplying by numbers that you measured by. So 25.0 is our answer. Put a little identifier there. Okay, moving on, and I'm going to take this little area here, my formula mass, and make that small. Move that over, and I'm going to draw a little red little line here to show that we use that to figure out this conversion. Okay, and I don't think we need this anymore. Okay, all right, moving on. So number 5, calculate the grams of salt. Hey, that's what we're finding. The ammonium dichromate needed to react to produce 256 milliliters of nitrogen. So in this problem here, they're giving me the volume. And then you want to work back into the salt. So if you go back to the original equation, they're giving me the volume of nitrogen, and somehow I'm supposed to predict how much of the original salt I need to make that amount. Now I can see it's a 1-to-1 relationship. So party people, that's what we're going to do here. We're going to do and use that relationship. So I'm going to start with what I'm given here, and this is going to be 200, and let's make that a little darker. So 256 at 256 milliliters of N2. It's always good to write down exactly what's given to you and of what chemical, since we're changing chemicals through the reaction using the mole ratios. Okay, well, one thing we need to understand is that I need to get these milliliters of this gas into moles. I can actually use the milliliters because milliliters are proportionate to the mole ratios, if you remember the boxes from Gay-Lussac. But just to keep things simplified, I'm going to convert this into moles, but I don't have a nice conversion, except when I looked at this problem, they gave you a really important piece of information. And let's kind of clean some of this up here. Some of this information is, this reaction is occurring where? At 0 degrees Celsius in 1 atmosphere. So my friends, in chemistry, this is STP, standard temperature and pressure conditions. And you should know something. There's an equivalent to volume, and that is 1 mole. Let's change it up. So 1 mole of any gas at STP is equal to 22.4 liters as long as we're at STP conditions. Well, we are. They kind of snuck it in the first line. So let's convert this to liters first, because we know the mole to liters, and that's easy enough. There's 1,000 milliliters in 1 liter. Liter's a bigger unit, smaller number. Smaller unit, milliliters, bigger number. And milli means 1,000, so you need a thousandth. So you need 1,000 of them. Okay, moving on. Now I'm going to use a conversion. I'm going to get rid of the liter, because liter's on top here, so I'm going to write 22.4 liters equals 1 mole. Good. And we can see that we're going to cancel milliliters, and we're canceling liters, and what's left standing is moles of nitrogen. Great. But they want grams of salt, so what we're going to have to do here, we're going to have to get rid of N2. Now that we have moles, which is a how many number, there is 1 nitrogen to what? 1 of these NH4 ammonia dichromates, Cr2O7. All right, so it's a 1-to-1. So we cancel out this. What unit's left standing? Hey, moles of ammonia dichromate. Well, we want grams. Well, we have the what? We have the technology to answer this. We have the formula mass. So we're going to get rid of mole. 1 mole goes in the bottom. And what's the formula mass? Hey, there's 252 right there. Okay, we're going to use that here as well. Same exact, oh, Christmas in July. So we're going to use that here as well. Any case, I don't think I like that. Let's kind of move this so it's kind of crunching on each other. Ooh, Christmas in July. Maybe I'll move. Oof. We can change that. All right, so 252 grams. 252 grams equals 1 mole. And let's get that going here. So we have 256 milliliters divided by 1,000, using my calculator, times by 1, divide by 22.4, times by 1, divide by 1. You say, why do we do that? We're keeping track of our units. And then times that by 252. I get 2.88. What units are left standing? Grams of ammonium dichromate. All right, and that's my answer in all of its glory. All right, and next one says calculate the number of hydrogen atoms produced in the decomposition of the salt if 47 grams of H2O was produced. Now, that's a different question here, because now they're giving us information about water. Okay, so if you look at the reaction again, the reaction's a key. They're giving information about the water. Oh, I think if I didn't read that correctly, my own problem. So what they're saying is, oh, okay, so they want the number of hydrogen atoms produced if 47 grams of water was also produced. Okay, so if 47.5 grams of water was also produced, okay, then we're going to take the 45.7 grams. Now, the water being produced here is a product And we assumed in the reaction that all the salt did decompose and burn like the picture shows. So this is really just a conversion, right? And notice they want the number of hydrogen atoms. That's a different question. So all of the water produced represents represents, in this case, in this example for this question, represents all the water produced from a certain amount of ammonia chromate. Okay, so this part here is tricky because it's produced in the decomposition of the salt. Okay, well, if water is produced, where are the hydrogen atoms? The hydrogen atoms, okay, are all in the water. So assuming that our salt completely reacted and we got that 40 some odd grams of water, 45.7, then all the hydrogen that was in the original salt is in the water. How many hydrogen atoms? So we're going to convert this to moles. And that's 18 grams per 1 mole. Mole of oxygen is 16, each hydrogen is 1. 16 plus 1 plus 1 is your 18. And then, because it didn't say how many moles of hydrogen atoms, they want to know how many, but careful here. Careful, careful, careful. It's not about the moles of water. Right now we have moles of water. So we're going to do some stoichiometry here. Now this is stoichiometry within the formula. So in every 1 water, let's keep it color coordinated, there's for every 1 H2O mole or particle, there are 2 H atoms. So the water cancels, and the unit left standing is moles of hydrogen atoms. But they wanted the number of what? Hydrogen atoms, not the moles. We'd be good to go solo if we had that there. They want the actual number. In our mole diagram, we can convert from grams to moles, moles to grams. As we saw in question 5, we can convert from liters to moles directly if we're at STP. If we're not, we're going to have to use the gas law equation that we'll learn later. But we can also convert what the mole represents. The mole is a word that represents a number. So now we're going to have to use Avogadro's number here. Notice where the mole is. Okay, so we're going to get rid of a mole. 1 mole is equal to how many particles? And this deserves a new color, don't you think? So we're going to go here with red. And so 1 mole is equal to 6.02 times 10 to the 23. That's the number, okay? And so notice moles cancel. And what units are left standing? Okay, how many hydrogen atoms exactly? Yes. So that's where the Avogadro's number comes in, because they're asking for the actual number of the hydrogen atoms. And therefore, we also, just understand this, we had to convert the moles of hydrogen, of water into hydrogen atoms by this ratio here. So let's go get that number, all right, and finish this worksheet up. So 45.7 divided by 18 times 2 times Avogadro's number 6.02, second function e to the 23. And what I get, you're going to get a very big number. Okay, we're not using moles anymore, which is a shortcut for these huge amount of particles it represents. We actually want that actual big number. Why is it big? Because these particles are so small. So I get 3.06 when I round to 3 sig figs, because I started with 3, times 10 to the 24, and it's hydrogen atoms. Hydrogen atoms here. And I'm just going to move this over, and to give myself some room so I can write that hydrogen atoms there. And there we go. All right, I hope that helped in a big way. See you next time.